All right. Thank you everyone for attending the webinar. I think we will get started. So I would like to first introduce the speaker. I've had the pleasure of working with SH for almost 15 years now. SH has over 30 years of experience in microscopy, material characterization, and instrumentation in diverse applications from material science, geomaterial research, to semiconductor failure analysis. He is an expert in X-ray microscopy and has published several papers in material characterization and imaging in the field. SH was a key executive responsible for the X-ray microscope company X-Radius' success prior to its successful acquisition by Carl Zeiss in 2013, and he is now the Vice President of Business Development at Sigray, which is focused on the development of ultra-high brightness X-ray sources and advanced X-ray optics, as well as laboratory instrumentation enabled by these technologies. So thank you, everyone. And SH will be giving a talk on advancing battery and catalyst research within Operando and multi-modality approaches. SH, you want to take it away?
Yep. Thank you, Sylvia, and good morning or good evening, wherever you log in from. So today in our webinar series, we're going to talk about all these advances or advancing battery and catalyst research. So we're going to focus today on in Operando operations and as well as the multi-modality approaches. So to start off with, let's take a look at a battery. And the battery is in operation under charge-discharge cycle. It do not run indefinitely because after a while, things will start to break down and anything that can fail will fail. Like for example, you look at this schematic, the anode and the cathode will fail. They will crack or there will be decompositions, and also the binders as well as the separator, all of them have different modes of failures. And how do you observe them? It is not simple because there is no one tool that will be able to deal with the problem. So you must be able to look at, first of all, from the scaling issues. Like for example, a battery is a relatively large object, but then it has components that go down to nano size. So you need to do multi-scale type of imaging in order to look at structural composition. Then you have different phases, multiple phases. You have electrochemistry aspect of it. You have different materials like polymers or ceramics, and also different type of elements from metal oxides to low Z materials. So therefore, to approach that, you need multi-modality, several different types of equipment studying the same effect at same point of time is possible. So therefore, to do that, you need to introduce another component for this type of research is that because everything is dynamic, you are looking at the dynamic evolution of materials and structures. So therefore, whatever you research, ideally, it has to be non-destructive, and you have to be able to do things like in situ or in operando experiments. So with this, it is going to be a tall order to really understand the whole process of battery or catalyst research. So if you were to do a review of the literature that's out there about how do you do battery research, inevitably most of the publications will originate from the synchrotron. For instance, in the synchrotron, they have X-rays techniques that will study electrochemistry, that will give you the ability to look at imaging or the structural compositions, and diffraction, look at bond lengths and changes in the lattice, as well as spectroscopy. And why they may be laboratory equivalent system to study most of these type of characters or characteristics or properties, you find that why do researchers have to go to synchrotron? The answer may be because of the huge limitations in laboratory techniques. Like for example, the source or the X-ray source in typical X-ray laboratory equipment is very weak. That means it's very low flux. When you don't have enough brightness in the X-ray source, you would have very poor sensitivity and throughput. And sometimes they go to synchrotron to overcome this, as well as they need a smaller spot size, a smaller X-ray spot size, or they need the energy tunability that is available in the monochromator of the synchrotron. And most importantly, many people go to the synchrotron in order to study things in situ or in operando. So if we were to look into the last topic on in operando, that's the main focus of our webinar today. And if we were to do a literature search again, you find that you don't see in operando using X-rays in most of the techniques. And most of the in operando experiments or analyses are done in the synchrotron. So the recent publications that just came out from energy storage material give you this type of overall review as to what has been done in operando using X-rays. So today I'm going to show you that it is possible now to do many of these type of characterizations for battery and catalyst in the lab itself. For example, whether you're looking at electrochemistry, like using X-ray absorption spectroscopy, or looking at structural imaging, like X-ray microscopy, or looking at elemental compositions, uh, uh, like very trace level compositions all the way to low Z. It is possible to do these things in the laboratory right now. And also, the other technique that is very common in the synchrotron to study battery and catalyst is in XRD, where you look at crystal structures. So today we're going to look at the three main area: X-ray absorption, spectroscopy, X-ray microscopy, and XRF, or elemental composition. How is it possible that we can now study these type of materials in the lab? And the reason it is possible is because of the emergence of disruptive X-ray components that give X-ray tools in the lab a tremendous boost in performance. And what made it possible is the patented X-ray source that Sigray produces, which has tunable energy. Not only is the X-ray tube very bright with small spot size, it is capable of having multiple X-ray targets so that you can select a particular energy from the click of your mouse to be able to change energies just like what you can do in the synchrotron. And when this is matched with a X-ray optics that again is produced by SIG or manufactured by Sigray, which is actually used by many synchrotrons around the world currently to replace, let's say, mirrors like KB mirrors. If we can match that X-ray source with the optics, now you have the ability to come up with a suite of X-ray techniques or X-ray instrumentation that has performances equivalent to the second generation synchrotrons. So today we're going to look at X-ray, the spectroscopy side, looking at X-ray absorption spectroscopy, notably in the fluorescence X-ray absorption spectroscopy. We also look at areas like imaging, where we have a unique tool right now to address structural evolution of battery material, notably pouch battery materials, if you are working with a relatively large and flat type of samples. and we can do that in minutes, so that it's possible now to catch the changes in the structures. And also for those who are looking at the elemental compositions, that is very sensitive. So we have a X-ray fluorescence microscope where it is possible to have performances very close to the synchrotron in terms of the detection level. And this will be able to go all the way down to low Z elements. Let's now look at what is X-ray absorption spectroscopy, especially for those who are new. Like for example, it is a tool that will probe oxidation states, bond length, and coordination numbers of elements. And these two are predominantly installed in synchrotrons, which with the techniques called XANES and XF, we're going to come in a moment. Like for example, in the synchrotron, the XAS beamline is the most competitive. This means there are very few people who have access to an XAS beamline simply because of the competition. And it is also the beamline that generates the most number of publications. And why? Because it has applications in almost every market segment, from batteries to catalysts to semiconductors, electronics, nanotechnology, mining, or biophysics. And also, it is versatile. This means you will be able to look at the materials that are not only crystalline, you can also look at amorphous. And if you look at amorphous, why amorphous? Because if you run XRD to look at bond length, you can only do it if it is a crystalline structure. What if it is changing? What if it becomes dynamic, especially in Operando? The material become amorphous, and you don't have tools to be able to study that, but the XAS is the go-to technique that will be able to deal with those changes. So XAS can also run in ambient or in vacuum. And why most people are operating their XAS research in the synchrotron is because there isn't any practical or high performances laboratory-based tool until now, which we are going to show and share with you in this webinar. Let's go back to battery or catalyst research. What is X-ray and why X-ray absorption spectroscopy? You find that it is very what you call versatile, because you can study very specific element all the way, whether you want to do the K shell or the L shell absorption edge. And you can also tune into the different sites. For example, the traditional battery material that is used commercially is still the lithium iron phosphates. We cannot study the lithium, but we can look at the other sites like the iron or the phosphorus component, and you can tune specifically into them. Next, the thing called XANES will allow you to study oxidation states or the valence states, whether the iron is 2+ or is 3+. And also, the XF will be able to study bond length, coordination number, and neighboring atoms. And this is a technique that can do in Operando during electrochemical cycling. So it is pretty powerful. It can apply to battery. It can also apply to catalyst. Now, let's take a look at what is this XANES and what is this XF. So every element will have its own characteristics, what you call chemical age. It is the energy where when you impinge a material with a specific energy of which a certain absorption is going to take place that is very sharp. And that is called X-ray absorption. And this X-ray absorption is called X-ray absorption near-edge spectroscopy, where you are going to study the age and the pre-age shift. I'm going to show you what is the age and the pre-age in a little moment. Like by studying the xanes, you can derive the oxidation states or the valence states. And this is due to the internal local structures from the multiple scattering. And then the next thing we call is the except, where you are studying the neighboring atom information, just like here, where the neighboring atom is going to influence your absorption. So this is called extended X-ray absorption fine edge structure, or XF, which is a gentle oscillations that is detected from the scattering due to the reaction of the neighboring atom. And this scattering can extend up to 1,000 electron volts. So therefore, it will continue to run. And even though it looks like what is there, how can you derive much information? We're going to show you how this type of oscillation actually give you information on bonding, on coordination number, and also on neighboring atoms and the extent of disorder. Let's take a look now at a deeper dive on what is xanes. Let's say I have a set of chemistry or chemicals based on iron. We have iron 2 chloride and iron 3 chloride, iron 2 fluoride and iron 3 fluoride. And we run an X-ray absorption on this this material. You find that the absorption age of the element of interest actually shift according to its chemistry. You can see that the higher the atomic, the oxidation number, like iron 2 to iron 3, the shift is towards the right. And if you look at iron 2 chloride to iron 3 chloride, again, you see the spectrum shift towards the right. And if you take a look, every one of them have a unique fingerprint, just like FTIR. You have a unique fingerprint in absorption spectroscopy. So, and also because you are looking at the age and pre-age, this is the age and this is the pre-age, the little bumps before the sharp absorption age is called the pre-age. They require your energy resolution in your tool to have pretty good resolution in order to capture all these little shoulders within the spectrum. So whatever instrument you have needs to have high resolution for the xanes. Like for example, ideally it should be 1 eV or less to measure. So in short, xanes allow you to look at the valence states like oxidation states. Now, here's another example. Let's say if we are given, let's say, iron in the material. Let's say you look at the SEM and the EDS, it says that you found iron. Now, my next question is that what type of iron do you have in that material? Is it elemental iron, that means has not been oxidized? Or is it the oxidized iron? Or is it a nanoparticle iron? How do you distinguish? You will not be able to distinguish using XRF or EDS. You have to go into absorption spectroscopy that will tell you whether this is a metallic ion or a oxidized ion or a nanoparticle ion. So same thing applies to manganese. And in this case, you see that the manganese, as it goes from your 2 plus to your 4 plus, you are starting to, the curve starts to shift towards the right. And you also can see pre-age in that transition, all of which will tell you very specific information about the two. So now what is XF, right? It is the oscillation that we talk about. It is caused by the interference from the neighboring atoms. But if you were to look at all this oscillation, though you do not see much information, but when you do a Fourier transformation on that spectrum, you find that you can distinguish the information that comes from the first shell versus the second shell versus the third shell. And from there, you can derive your interatomic distance, your coordination number, and also the mean square disorder. So therefore, XF gives you bond length, number of neighboring atoms, the atomic number or the nature of the neighboring atom, and the coordination number or the number of atoms at a specific distance. So at this point, there will be some of you may ask, okay, I see some of these things can be done with XPS. Now, what's the difference between XPS and XAS? XPS is found in the lab, so many people are familiar with it. So XPS basically measures your binding energy. It is a measure to measure or study things in the surface. Surface chemistry or contamination studies is very useful using the XPS. It also gives you some elemental composition of the surface. Whereas in XAS, you are looking at the ability to look at oxidation states, density of the elements from the surface to the bulk of that material. Things that are bound to the atom of interest, bond lengths and other things, and it can do in operando type of characterizations that is not possible with XPS. So to summarize that quickly in a table, we will say that XPS is excellent for surface composition and surface contamination, is not for bulk. In fact, XPS only look at the top few nanometers of the material, and it is not possible to do in operando type of studies, whereas XAS or XANES and XF gives you the ability to probe not only the surface, but also the bulk. And you can do in operando studies using XAS. And XPS people know more because it's laboratory based, whereas XANES are often only available in synchrotron where they are doing real practical studies. Except now it is possible to be able to do the studies that in the past can only be done in the synchrotron. And you will look at XPS because they require ultra high vacuum, 10E7 to E12. So it is extremely susceptible to contaminations that are introduced, and therefore they are generally not used for real world samples. Whereas XANES or the SF, you can run it in ambient, in vacuum, in high temperature, and high pressure, and in operando to mimic the real operating conditions. So in summary, if you're looking for surface-related studies, XPS is the go-to characterization tool. It's good in battery for surface films, for SDI layers, and also the surface states of catalysts. But if you are looking for bulk properties or dynamic process, and the ability to do in operando experiments, there is nothing that can beat the XANES and the XF because of their diversities and ability to solve this type of problems. So if you are looking to develop an XAS tool that is practical and has synchrotron type of performance, so you don't have to always run to the synchrotron to do those studies, then there are certain, let's say, criteria that might be useful. And those are the same criteria that Sigray has been using as we started to commercialize and develop this tool. The tool must be able to do transmitted image. This means you have a sample in, the X-ray must be able to penetrate to, and you have a detector that measures the transmitted X-ray absorption spectrum. You must be able also to look at the fluorescence side under the reflection mode. So therefore, if we were to summarize this, an XAS tool that is practical must have the transmission mode and the fluorescence. Why transmission and the fluorescence? If you have a lot of pure samples, more than 5%, transmission will be okay. But what if you have less than 5% of the material of interest? Or what if your sample is dilute, you're working with a thin film, like in semiconductors, you're working in the liquid, then you have no choice but to run it under fluorescence mode. That's what they do in the synchrotron. Next, it must have high resolution ZANEs, must have high throughput XF, must be able to image from soft materials all the way to relatively hard materials, including those that are in the acetinide and the lanthanides type of things for those who are doing nuclear type of research. And also it must be able to support in situ or in operando operation. So to look and address the need for the XAS community, Sigray came out with two models or two products. One is a vacuum base that can run from 1.7 keV to 10 keV that has this particular geometry where we can now study materials all the way perhaps down to silicon. Next, this is the workhorse, the Quantum Leap H2000, which have energy levels from 4.5 to 25 keV with a scanning geometry and a very low Bragg angle. So, large Bragg angle, so that for we can solve a lot of it's called low Bragg angle that allow us to solve many of those issues that are facing the characterizations of battery and catalyst. For instance, this is a schematic of the H2000, which is designed to look at the low Bragg angle operation and also have a patented high brightness X-ray source that has tunable energy. And it allows us to run it under transmission mode using a photon counting the detector, as well as using the SDD detector to look at the fluorescence mode. We're going to see that it can cover a wide range of materials. In fact, 75 elements can be covered using this particular equipment, from titanium all the way to high Z elements. And one of the innovations is that of the X-ray source that has tunable energy. Not only it has very high brightness, it gives you the ability to have multiple targets and have a small spot size, and with the choice of numerous targets available. And that is important, especially in XAS, where you are not using the characteristics line of an X-ray spectrum. In fact, that is the area we have to avoid. We have to use the Bremsstrahlung, the much lower intensity part of the X-ray spectrum, in order to get the range that we need, notably during XF type of collection. So for instance, we can switch from one energy into another energy so that you can have a spectrum that is free from the characteristics line, whether you are working with elements from 1.7 keV or 25 keV. And that is a high power X-ray tube with 500 watts and with multiple energy source. So here are some results. We can get high energy resolution. In fact, we can even look at the pre-age of the rutile that match the synchrotron. Next, you can have high throughput, which is ideal for fingerprinting of material for in situ studies, as well as you can cover a broad spectrum of research for different elements. Like for battery research, majority of them are transition elements, but then for catalysts, many of them are higher Z materials. So that we can cover. And the high brightness with tunability has been able to match very well synchrotron data with their high energy resolution, or looking at bond length informations or coordination numbers, we again have been able to match them. And these studies takes only minutes rather than days very often, because of the high flux that is possible without equipment. We're going to show you some studies using the NMC type of material. The predominant chemistry that is in the commercial batteries are the lithium iron phosphates. But the ones that is undergoing a lot of intense research is the NMC, or the nickel manganese cobalt combination. So NMC 111 is actually, or NMC 333 has 33% nickel, 33% manganese, and cobalt 33%. The next generation is that they'll try to reduce the cobalt and the manganese and increase the nickel. So they came up with a combination called 622 with 60% nickel, 20% manganese, and 20% cobalt. And the 811 is 80, 10, and 10. So these are the three generations of NMC battery with increasing nickel concentration. So we did a run to show that, okay, if you run all these three, you find that there is a shift in the oxidation state from your 111 to your 811, where you see the nickel is shifting towards the right because oxidation states have increased. And what if now we study the cobalt aspect of the cobalt side, or the cobalt moiety of that NMC? You find that you don't have that shift in the cobalt because the cobalt oxidation state has not changed as you go from your NMC 111 to your 811. What if you have samples that are very concentrated, that do not have the concentration? This means they are very low concentration, they are dilute, or the samples become very thick that is impossible for you to have the X-rays to go right through the sample under transmission mode. So in those cases, in battery or catalyst research, it is very common. How many of you who are doing synthesizing all these catalysts or materials can get high concentration? Most of the time, you would not be able to get a high concentration, high concentrated or a more pure material. So that is not possible to do transmission mode. So what if you also want to study the non-dominant part of the material like MMC? The manganese and the cobalt of the MMC are in the minority. If you were to study them, they will be the concentration is much lower compared with the whole material. What if you are dealing thick samples or highly absorbing samples, as well as those that are where you are trying to run in Operando studies? So for all these materials, you will need much greater sensitivity, and we can do that under fluorescence mode. So the quantum leap can analyze materials less than 1% weight or 1% weight under the fluorescence mode. And we have done that to something as low as 0.2%. So let's take a look at some of the studies for the NMC, looking specifically at manganese and cobalt in a nickel-dominant material. So here you can see that the manganese under charge-discharge cycle and the cobalt under charge-discharge cycle can be studied under the fluorescence mode. But the most important part that we want to share with you is, can you do in Operando studies using XAS, and do you have anything to prove that you have done that? And we have basically done that. We have built in Operando cells that can run in high temperature or can run under different type of conditions. So here is a latest study that we have done in Operando using our laboratory system, going through 10 charge-discharge cycles and tracking them. And you can see that we can do that in a coin cell under all the cycling mode, and at the same time collecting our XAS data. And you see there is a notable shift as it goes from your 2+ to your 3+. So that data or that study will be published. Next, how do you solve real-world problems that typically that's why people go to the synchrotron, to be able to use the synchrotron XAS to solve real-world problems. What do I mean by real-world problems? Problems that simulate your actual day-to-day research. So here we have a 4 different MMC material, and we want to identify the speciation of the cobalt when it is doing the running the charge and discharge, and the percentage or the concentration of the cobalt in this case is less than 2%. And one of the things that we want to point out is the ability of the laboratory systems to identify isobastic points. What are isobastic points? Is where the wavelength, where the absorption or absorbance of 2 or more species intersect or are the same. So the appearance of this isobastic point in the reaction generally means that an intermediate is not required to form a product from a reactant. So the laboratory tools demonstrated high stability and reproducibility to obtain 3 isobastic points here, as you can see in this figure. Later, as we run the other experiments, we can see which one or which of the set of data is the most oxidized and which one is the most reduced. So you can see that sample number 2, the red one, is the most oxidized because its curve is shifted all the way to the right. And the sample number 1 is the most reduced form. So you can see that from the most oxidized from the most reduced, there is a delta of 0.7 EV oxidation shift. So this data can be done because the system is highly sensitive and highly stable and reproducible. And because of the reproducibility of the data, now you can apply techniques that you generally only use in the synchrotron, like PCA analysis, like principal component analysis, or the ITTFA, or the least square linear combination analysis. All of them are used because multiple species are generally formed during in Operando reaction or during a charge discharge cycle. So the ability
probably to add to what SH is saying, another reason why this study was so interesting is on a very modern NMC battery, the cobalt that we're measuring is far less than 2%. So it's an extremely challenging set of samples as well.
Yeah, thank you, Sylvia. So this ability to identify very dilute samples or the very low concentration sample becomes very exciting and powerful, that made it possible that the laboratory system might be able to do many of those experiments that currently can only be done in the synchrotron. And by being able, by having very stable and reproducible results, now you can apply all these techniques that are only obtained in the synchrotron. So I'm going to switch and show you an example of catalyst. Here in this case is a platinum catalyst. There's a hexagonal boron nitride catalyst, and you can run this thing, and then we run the XF, and when we do the XF, we do our K all the way up to 14, which is which means that if your data is usable up to K equals 14, therefore the stability as well as the accuracy of the data can be trusted. So using the fitting algorithm, we have been able to identify the coordination number In this case, the platinum nitrogen bond, the platinum bond at the 1.2 and 5.5 respectively, and also the interatomic distance as well as the level of disorder. So all these techniques are actually very comparable with what we have done in the synchrotron. Now, to summarize, what the XAS can do is you can have a near complete periodic table coverage from 4.5 to 225. And for those applications that require softer or lower Z elements, we have the vacuum-based V210, which I do not have time to cover today. And you have high flux on the samples for fast measurement. You have high energy resolution. And this tool is easy to operate. It's not like a research tool where you have to change crystals. In fact, it's all automated. Our computer can change the crystals automatically, and only 4 crystals are needed in the tool to cover the full range, as well as we can do in Operando experiments as we have shown. So now let's go on to look at what are the other modalities that is very necessary to do battery and catalyst research. That is structural imaging. So in X-ray microscopy, because the material is a macro system all the way to nanosystems, you need multiple tools from X-ray microscopes to your FIB-SEM, to your STEM, from your TEM, in order to cover the full range. But then we are just focusing on the X-rays because that is the non-destructive part of the characterization. So for X-ray microscopy, we have 2 products. One is the Eclipse, which has the 300 nanometer spatial resolution, and the Apex that we're going to focus more today, where we can run up to 500 nanometer spatial resolution, but for planar samples, especially for pulse battery during in Operando experiments. Here is this traditional type of work that we have done in the publications, where we can zoom in from a whole lithium-ion battery and look at all the deformations and the defects from the cathode materials to the collectors to look at voids and delamination. And we have been able to identify the various type of failure mechanisms, from impurities to non-uniform packing or delaminations or deflected electrodes or cathode or burrs on the tab. So now let's take a look at the in Operando or in situ experiments. Here is a simple example where we are looking at the electrochemistry during the deposition or nucleation of zinc dendrite on a copper mesh. So you can study nucleation in 3D, and from there you can derive the various mechanisms where it's shown that during early nucleation, the T or the time is slower, but late nucleation, you find that there is an avalanche of all those precipitation that has happened, and all these dendrite formations can now be modeled in situ. But then when we want to do, let's say, in situ or in Operando on, let's say, a real sample, like for instance, what if you want to study a pouch material or pouch cell? You find that if you run this under the conventional X-ray microscope mode, you will see what you call loss of streak and loss of noise, like what we see here, using a traditional X-ray microscope with a 20x objective lens. And you see streaks, and where these streaks, then it's impossible to do quantitative measurements of the size of the pores and to even identify where the locations or the defects are. So this is due to what you call beam hardening effects that those who are doing X-ray microscopy or micro-CT will be very familiar with. Next, to solve this problem, we designed a novel tool that can work with large samples, therefore pouch batteries or wafers or PCBs can be inspected very fast, from a few minutes to an hour, with a resolution down to half a micron. This is a schematic of a traditional 3D X-ray microscope. So if you have a flat object, obviously you find that you have to space the source from the detector quite far away during the rotation. And what if when this material is right in alignment with the source and the detector? The X-rays has to go all the way through a lot of materials, and that gives rise to huge amount of artifacts called beam hardening artifacts. Now, it is also very slow during this, using this type of traditional approach where the sample is rotated this way. So what we have done is we have a patented architecture which allow us to spin the samples and the X-rays come in at an angle. And with this, we can see that we can inspect a battery, traditional pulse battery, from 4 hours all the way to 12 minutes. You don't see a change in the details that is necessary for you to identify defects. And also it can run at pretty high contrast to be able to identify the graphite from the solid interface, from the silicon and from the void. And here is an experiment or a publication for in Operando pulse cell experiment using the apex. So you see that in this scenario, using the new type of architecture, is a modified laminography technique, we have been able to see all these details of the grain structures in the electrode and be able to color code them to during segmentation in order to give you quantitative measurements of their diameter from the graphite materials to the MMC materials. So that is without beam hardening using this technique, and you can now observe the multiple degradation mode within this pulse cells battery. So the last part, with the remaining few minutes, I want to talk about the XRF or X-ray fluorescence microscopy, because we are actually have the ability to image elemental compositions down to a few microns spatial resolution using this technique, and it has the glazing angle in order to look at many low-Z material. In fact, this tool has won the Microscopy Today as an award, innovation award winner for being able to look at trace level compositions down to sub ppm level because of the architecture. So with that geometry, with a high vacuum, 10 minus 5 tall, and we have been able to look at low-Z materials such as aluminum, all right, magnesium, sodium, fluorine, sulfur, and phosphorus. It improved the detection level over traditional micro XRF, and also it beats everybody else in areas like organics, carbon, oxygen, nitrogen, where we can get down to sub 0.01%. In contrast, what is the concentration that you must have to detect an element under your SEM EDS? You need at least 1% before they can be detected. So these two allow you to not only look at sub ppm, but you can go all the way down to your organics. So what makes it possible for us to detect all these things so well is because of the ability to shift energy according to what we want to analyze. For instance, if I'm interested in aluminum, now if I use a wavelength or the energy of a molybdenum, this is the fluorescence cross-sectional U, or you may convert that into the count rate. Let's say you may have only 5 counts, but if I shift my target of the X-ray tube to copper or 8 kV, we got 10 times improvement but it's still very misery, because 51 counts is not going to do you a lot of good. What if you now go to chromium? Now you have jumped up to maybe 30 times better than your molybdenum. What happens if you now shift to your silicon? You find that you got the sharp increase of up to 644 more times. So in other words, you will be able to increase detection level dramatically without having to change other hardware or software or algorithm. That's as simple as that. That's the reason why it's so powerful in the synchrotron. And you can do that in the laboratory right now. So an example is the space agency sent us a sample for aerospace application to look for impurities. So everybody else might be able to look at silicon. Some of them can see oxygen, but then everything else they cannot detect. But we have been able to detect all of these trace elements very easily using this tool. This means the sensitivity is much, much better than the traditional systems out there. So this high sensitivity down to sub-ppm level can be effectively leveraged in the battery industry. We can locate impurities that are picked up from different manufacturing lines. For example, if you find iron and chromium, therefore you have the ratio of a stainless steel from a certain machinery. Or if in the NMC battery production, if you see traces of hafnium or zirconium, then you know that it must come from the zirconium mill balls in the process. So here in the example of looking at impurities in the lithium cathode, where you can see you can see the different type of detections, and also you can see the iron and chromium, and also you can see zirconium and hafnium. So identifying where the actual source of contaminations came from. So you can also detect the migrations of the transition metals onto the graphite anode. And these are all examples of papers that we have published. So in conclusion, we have shown you a suite of laboratory-based equipment that can study your chemistry for batteries and catalysts, and be able to operate under cycling, like charge discharge cycle, using in situ cells. We also show you different types of X-ray microscope systems, including a system that can run in Operando for large pulse flat battery materials, and also the XRF system that has performance very similar to what you see in the synchrotron XRF. So with this, I would like to stop here and open to questions. Are there questions, or you can type your questions in the chat?
Well, if there are no questions, thank you, SH, for that excellent presentation. If you have any other questions, you can email us afterwards. You likely have my email by now, as well as SH's. And otherwise, we can also send a recording if any of your colleagues are interested in the recording. All right, thanks so much. Bye, everyone.
Yeah, thank you.